everyone, my name is Menachem Rose from Esri, South Africa. I work on artificial intelligence and machine learning applied to geospatial data. I'd like to talk today about machine learning, what it is and when to use it. We'll be covering the key terminology and the general concepts behind machine learning and deep learning. They're important buzzwords at the moment. And we are going to cover some important use cases of machine learning. We will not be talking about the complex math and computer science which underlies machine learning. The math can get quite challenging, that's not the focus of today. And we will also not be going into the details of the algorithms used in machine learning. There are many commonly used ones and even more not commonly used ones. That's not the focus for today either. First, we need to define our terms. And the first term I'd like to define is algorithm. An algorithm is just a specific series of steps with a particular goal in mind. So a very simple example of an algorithm would be, if you want to obtain the average price of stocks in your portfolio, you need to add together all the stock prices of all the stocks in your portfolio and divide that sum by the number of stocks. That gives you the average price. That's an algorithm. It's a very simple algorithm, but it is an algorithm. The natural question then is, if that's what an algorithm is, why is it that only computer scientists use the term? Or the only ones that use the term frequently? And the answer is that it's true, algorithms are all around us, but we don't focus on them. In computer science, we deal with computers. Computers don't have common sense. When one's dealing with a person, one can explain to them the goal of the algorithm. And then the exact formulation of the algorithm itself is not that important. We can rely on the person's intuition and common sense. But to quote Arthur Bloch, a computer program, it does what you tell it to do, not what you want it to do. It doesn't have any common sense. All it has to go on is the algorithm. So the exact formulation of the algorithm, that is critical. The next definition which is important for us is model. A model is a system used to make decisions or predictions. If one worked in weather, one would develop a model to predict the weather. To go back to our stock paradigm, a simple model in stocks could be, if the average stock price in the portfolio dips below 100, sell. It's a very simple model, and we all hope that our stock advisors have more advanced and more sophisticated models than that, but that is a model. And to compare those two terms, a model can contain many algorithms. So here we have model KM50, sounds very important. And it contains, in this case, 3 algorithms. And the algorithms can work sequentially or they can interact, depends on the model itself. But the point is a model can contain multiple algorithms. The final term I'd like to define is methodology. A methodology is a guiding philosophy that could underpin many models. To go back to stocks, a stockbroker could have a quantitative methodology. He could crunch numbers before he decides whether to purchase a stock, or it could be industry specific. Or he could look at videos of the CEO doing interviews before he decides whether to purchase a stock. Those would be different methodologies. And a methodology typically underlies an entire business. An entire business has a unified methodology of how it approaches things. A final term which is sometimes used is process, and I think of process as synonymous with algorithm. We'll use the term algorithm in this presentation. Now that we have our terms defined, let's talk a little bit about artificial intelligence, or AI. AI is quite a large field, and it contains several subfields, including machine learning, but it also includes others. Machine learning itself includes some subfields, most notably deep learning or neural networks. We will use those terms interchangeably. One could differentiate between deep learning and artificial neural networks, but for our purposes, they're pretty much synonymous, and we will use them as synonymous. What is artificial intelligence? It's the study of programming machines to perform tasks which usually need human intelligence. And as I say, it includes several subfields like machine learning, but also robotics, natural language processing, And we're familiar with some of these from, perhaps we go onto a website and it says, "Hi, I'm chatbot, how can I help you?" That's AI, specifically natural language processing. There are generally two types of AI, strong AI and weak AI. They're also referred to as general and narrow AI. Strong AI is a machine that can mimic human reasoning at all tasks, and we're familiar with this from the movies. Weak AI, on the other hand, that's a machine that seems to reason like a person, but only at specific tasks. Strong AI doesn't exist in real life, it only exists in the movies. And to give you an example of what that might look like, if you turn on the news one day and you see computer wins Nobel Prize, that would be a pretty strong indication that humanity has achieved strong AI or general AI. To quote Yann LeCun, who's the chief AI scientist at Facebook and one of the godfathers of machine learning, "The technology we have today is nowhere near anything like human intelligence. It's a misnomer." He goes on, "I am optimistic we will reach it in a few decades." So strong AI is something that is being considered, but the impression that's sometimes given that it's just around the corner is a little bit misleading. What we have right now is weak AI, and that will be the topic of this presentation. Let's define machine learning as well. Enabling machines to make decisions without being explicitly programmed. That's machine learning. That's a paraphrase of a quote by Arthur Samuel, who's was one of the pioneers in the field. If we can enable machines to make decisions without being explicitly programmed, we're performing machine learning. And the key paradigm is that the computer is going to use rules to make decisions. So those rules depend on the initial data that it receives. The rules are not dictated explicitly by the programmer. The rules are instead gleaned from the data the computer receives. And we'll go into detail. An example of machine learning could be when a person assesses loan applications for a bank. And the criteria by which one assesses whether a loan application should be accepted or rejected, that set of criteria doesn't vary too much between loan applications, so it seems like a good candidate for machine learning, to apply machine learning to this problem. Now one could go about it in two ways. One could explicitly program the computer and say, assess the age of the applicant in the application, and if the age is below 21, reject it. That's not machine learning. That's what we referred to before as explicit programming. We've explicitly told the computer, if it's below age 21, reject. On the other hand, if one feeds data to the computer of past applications, which have been hand-labeled as accepted or rejected by an expert, and the computer learns from that data set, and then whatever rules it learns, even if it learns that exact rule of under 21 reject, because that's the trend in the data, that's machine learning. It's using the data to learn the decision-making process. That's the underlying paradigm of machine learning. From the data we feed the computer, the machine learns the decision-making process. How does it learn the machine-making process? The decision-making process. How does it learn it? The learning is done using the algorithm we specify for the computer. We will specify an algorithm which the computer will use to react to the data. If the data looks like this, react in this way. Be more lenient, be more strict. We must tweak the model in this direction. These are all specified by the algorithm, but ultimately it will depend on what the data that we feed into the computer looks like. The loan applications, in our case, we initially feed to the computer, along with those labels of accepted or rejected. That data is known as training data. Deep learning is a particular type of machine learning. And the key paradigm of deep learning is that it uses progressive layers of features, which we call neurons, in order to make predictions. And we'll speak more in detail about that in a moment. Deep learning can be used to perform many different types of machine learning tasks. It's not specifically geared for only one type of machine learning task. Another thing to note about deep learning is that it's not all that new a concept. It was conceived in the 40s and the 50s. But at that time we didn't have the computer processing power and we didn't have the data available in order to create sophisticated and successful deep learning models. But we have that now. Computer processing power increases almost by the day, and the amount of data that's created, there are figures that we create 2.5 billion gigabytes of data per day, and that figure is 2 years old, so it's almost certainly more now. So we do have the data and the computer processing power to make successful deep learning models. As I said, deep learning and neural networks and artificial neural networks, we will be using those terms interchangeably. Here's a map of machine learning. And there are different types of machine learning tasks. In general, they can be divided into two tasks. There's supervised learning and unsupervised learning. The key distinction there is, in the training data we provide the computer, is there ground truth, are there ultimate truth labels for this data? In our learn application data set there were. The person has to go and label each application. Should it be accepted? Should it be rejected? Those are ground truths. So that would be supervised learning. Within supervised learning, are we predicting numeric values on a continuous spectrum? Then it would be known as regression. Or are we predicting one of a discrete set of groups? Maybe we're predicting yes or no, or high, medium, or low. If that's the case, where we're predicting one of a set of groups, one of a set of labels, that will be classification. If there are no labels available, that's known as unsupervised learning. An example of this could be clustering. And perhaps we want to cluster our customers. Then we don't want to ahead of time say, customer number 9, he belongs in cluster 3. Let's see if the model can predict that. Because we don't want to dictate what group 3 is. We don't want to dictate how many groups there are at all. So we feed in data without any labels, and in the clustering example, and we dictate to the computer using our algorithm. We allow it to identify the clusters for itself. That's unsupervised learning. Now, deep learning / neural networks, there are several types. There's convolutional neural networks and recurrent neural networks. They can be used to perform supervised learning and unsupervised learning. To give an intuition into what deep learning is, let's go back to our typical machine learning example of loan applications. There, the bank employee implicitly told the computer which features it's allowed to use. It doesn't have to use every feature we provide to it. But if a feature is not provided to the computer cannot use that feature to predict. Then the computer combines the features to predict the outcome. But could we design an algorithm where the computer uses those features, those initial features, to construct new features? And those features perhaps will be better able to predict the final result of the loan being accepted or rejected. So this was our diagram from before. This was typical machine learning. It combines these features in different ways to create a prediction. But we could do this. Combine those features to give, instead of the final outcome, intermediary features, which is what I call here learned feature 1 and learned feature 2. And we use those features, intermediary features, to predict the final outcome. So here we have the input layer, the features we can see of age and applicant annual salary. We have the output layer, which is the prediction, whether the loan is accepted or rejected. And then we have a hidden layer of these hidden intermediary features, which the computer creates while making its predictions. This is the paradigm of deep learning. Now, there's no rule that we're only allowed to have one hidden layer. We could do this. We could have our initial features, combine them to create new features, combine those features to create new features, and combine those to create an ultimate prediction. So here we have learned feature 1 and 2, but those are then combined to create new features, learned features 3 and 4, a new hidden layer. And we could have 2 hidden layers, we could have 5, we could have 100. And some of the most successful deep learning models today do have dozens or hundreds of intermediary or hidden layers. Now, we can see from this diagram, and there will be another diagram here with the same model, essentially from a different viewpoint. We can see that this model is getting quite deep. We can understand the term deep learning, because we could have 2 hidden layers, like in this example, or we could have 20. So it becomes a very deep learning model, a deep machine learning model, and we call it deep learning. Why do we call it neural networks? Well, each of these features, each of these nodes is referred to as a neuron. And that interconnected web of those neurons is called a network of neurons, or a neural network, or an artificial neural network. Now, the architecture of an artificial neural network is loosely inspired by the neurons of a human brain. But again, it's loosely inspired. So some folks have the impression that there are psychiatrists on the AI team making sure that the deep learning models adhere to the function, how a human brain functions. That's not exactly accurate. The architecture is inspired by the human brain, but it works, and it can be, we focus on how to improve it on its own terms at this point. Neural networks have been very successful at interpreting images and video, and one could think about it in the following way. It's very difficult to look at an image and say, that pixel predicts whether it's a car. But what deep learning might do is say, this group of pixels, or that pixel, predicts whether it has a wheel. And that a wheel could be an intermediary feature. And if we have 4 wheels, then we use those 4 intermediary features of wheels to predict car. So that could be an intuition of why deep learning is particularly successful with images and with video. The requirements needed to produce a machine learning model are as follows. First, we need data, reliable data. And those who work with data know that the word reliable deserves its capital letters. But a machine learning model is only as good as the data it's trained on. We could well need data in huge quantities, because as we saw before, a deep learning model could have many, many neurons, many hidden layers, and each hidden layer requires data to train on, and in order to make sure that that layer is fine-tuned and predicting as well as it can. We'll also likely need machine learning knowledge. There are some out-of-the-box tools which can be used to build machine learning models, but we will need knowledge of machine learning in order to both to assess those solutions, and if those out-of-the-box solutions don't work, we need to know how to improve the model, how to assess where it's going wrong and why. So machine learning knowledge is an important component here. We also need expertise in the industry, and we need that in order to validate the underlying assumptions of the model. Every model has assumptions, and sometimes those assumptions are not explicitly stated, but they are there. For example, with stocks, a common assumption is that today's stock prices can be used to predict tomorrow's stock prices. That's a common assumption. That assumption needs to be validated. We need to assess if it's acceptable and if it has basis. Finally, we need rigorous testing, because again, the model is trained on training data for which it has the actual truth available. But that's not how it's going to work when the model is in production. When the model is actually being used, it's going to be used on data where we don't know the ultimate truth. That's why we're using the model. And we need to know ahead of time, how does the model react, and how does it perform on data that it's never seen before. So we need to test that. We need to keep a set of data away from the computer so it's never seen it before, which is known as, this data set is known as test data. And we need to assess how well the model is performing on this test set. So those are some of the requirements when producing a machine learning model. I'd also like to give a disclaimer. Machine learning is not a miracle panacea. It's not going to cure all of the world's problems in the next 12 months. The way to think about it is it's a very promising field of ongoing research, and that research is very hot at the moment. To illustrate that, according to Google Scholar, over the 5-year period between 2016 and 2020,
the most influential scientific journal was Nature. And in Nature, during that period, three most cited papers in Nature, three most influential papers, they are the most cited, were all related to machine learning. Specifically, they were on deep learning. So it's a very hot field of research at the moment. I also want to point out that machine learning is a tool and not a product. Sometimes people approach the problem with, I want to apply machine learning to this problem. A better approach would be, I have a problem, machine learning is a tool at my disposal, which I can use if it's the best tool for the problem. So it's a tool and it's not a goal in and of itself. Machine learning has already shown promising results at certain tasks. So I said it's a field of ongoing research, but it has already produced successful results at certain tasks. Some important use cases in general include tumor classification, real-time object detection, which is crucial for self-driving cars, for images and video, and there speed is important. Speed will have to come into that metric we talked about before, because it's no good having a model that's 100% accurate and it always tells you 10 minutes ago that object that was in the camera, that was a car, you should have stopped. Because it can be as accurate as it likes, that's not valuable 10 minutes later. So speed is important. We can also forecast stock prices and predict when customers will churn, as well as targeting recommendations like some popular streaming services use. We could also detect credit card fraud using machine learning. Now, with regard to tumor classification, some early results indicate that some machine learning models could be as accurate as medical professionals at analyzing medical imagery. Again, that's not going to replace doctors. Doctors will likely work hand in hand with the models to produce better outcomes across the board. And again, we will need more data to assess whether they're in fact equivalent with that. GIS-specific use cases include classifying land cover, detecting building footprints, spatial pattern recognition, and detecting change in one's imagery. These are just some of the use cases in general and GIS-specific. There are, of course, many. For those interested in learning more, here are some references and resources which are very helpful in learning more about machine learning, the details and where it's used, and how it's used, and how it's implemented, and some references to have a look at for the data on how much data we create and where the quotes are from and how many and how accurate people are versus models at medical imagery. Thank you very much for joining me. I hope you gained a lot, and thank you and all the best.